Happy Election Day, everyone. At least I hope it's a happy one.
I wish I could vote.
Okay. Any questions?
Oh, I have a question.
Yes.
It was just a question that was on the master set where we were given vectors for the initial speed, or I guess it would be the velocity. And in the equation 1/2 mv squared, the v would be a speed, correct?
Correct.
So would I have to convert the vector to like a magnitude, or can I put the velocity vector in for v in the 1/2 mv squared?
If you square a vector, the general rule is that you're doing a dot product with itself.
Mm-hmm.
So in essence, you're finding the magnitude anyway.
So it doesn't matter if on my, you wouldn't take points off of on my work, I just plugged the vector into the equation and then squared it and ended up getting, I know I would end up getting the same answer, but it doesn't matter how I show my work.
No.
Remember,
That's pretty good. Do you have any questions? We're asking questions.
Any questions over here?
You already answered my question.
yeah.
Any questions? Why?
I'm done.
Oh God.
Because it's been reserved for this. All right, I guess we'll figure out which ones are decent and which ones are not. All right, so what we're gonna do right now is double the number of equations.
Huh?
I think of all the equations we've worked with, we're gonna double it. Sounds like fun.
Very.
This will be chapter 9. Let's see, chapter 7 is energy, chapter 8 is momentum. So we're done with momentum, so let's go ahead and stick some of that stuff up. So this would be 12, 13, 14. Yeah. All right, so a week from today, master set 8. A week from tomorrow, homework quiz 8. And there we go. We're starting on chapter 9.
The master set for 8 is a conjoined one. It's like master set 8 and 9, I think. Right?
I thought 9 and 10 were joined.
Oh, then I'm sorry, that's my fault. No.
2 and 3 was velocity, position, etc. That's 2, 3, 4, 5, 6 was the last test. Was test 1B. 7, 8. Yep. I think we're good. All right. So here's how we're going to do it. We're going to start getting into rotational motion. Now we've dealt a little bit with rotational motion if the speed is constant, but the speed's not necessarily going to be constant as you go around a curve. So we do have 2 types of acceleration for something traveling where the direction and speed change. So far we've dealt primarily with linear or translational motion. These terms are pretty much interchangeable. Actually, I don't have a situation where they're not interchangeable. Just that tradition, we typically use the word linear or translational out of custom. Or, it's linear velocity, we don't say translational velocity. Although if you said translational velocity, it means the same thing.
Does that apply to only centripetal force or motion?
This applies to everything we've done except for centripetal, actually.
Okay. So there's linear and then centripetal. That's it.
No, we'll get to that.
Okay.
So why don't we start off with position. Now, we generally just say the position, we don't say linear position, it's sort of understood. But there is a rotational equivalent or angular equivalent, so rotational slash angular. And again, these terms are interchangeable. It's just that tradition has us using one more than the other in certain situations. Now the symbol for position is X, Y, Z, something along those lines. The rotational analog of position is angle. And it's typically theta, phi. Those are the two most common ones. Alpha and beta sometimes get used, although I will not use alpha for it. I guess I have used alpha for angle. Well, not anymore.
What about beta? You just said that. I'm sorry.
Theta and phi are the two most common ones. And I've probably mentioned, I know I've mentioned to at least one class, don't use pi as the symbol for angle, as I saw in one book, textbook. God, that confused me. All right. We have velocity. Actually, go in order. Displacement, where we just stick a delta in front of whatever letter we're using for position, and the analog over here, angular displacement. And it's just the delta in front of whatever letter we're using for angle. Now, typically in a problem, they're not going to ask you, they're not going to use the term angular displacement. I have seen the term and it is valid. However, generally, if you have an object rotating, you would say through what angle does it turn? That's more of the language that you're typically asked. Or how many revolutions will an object rotate? Velocity, the symbol will be the vector symbol, and the rotational analog, angular velocity. And the symbol is an omega, it's a lowercase omega. Now, at this point, hopefully, you're seeing a pattern here, is that the linear translational stuff are generally Roman letters.
Greek
And
letters.
what?
Greek letters.
The rotational analog are the Greek letters.
Yes.
Okay. I didn't know if you were jumping ahead or correcting me for what X, Y, and Z are.
I'm gonna leave that up to you.
Okay. I assume you were jumping ahead. Now, using Greek letters for rotation, rotational motion is typical, but it's not 100%, so we will run into some non-Greek letters at some point. Acceleration. A, the vector symbol, since we're talking about the vector quantities. And someone will take a wild shot at what the rotational,
Angular acceleration.
there we go. And the symbol?
Is it another Greek letter?
Yes, it is.
Is it an alpha?
It is.
Does it have? Yep, yes it does.
Which is why I won't use alpha for an angle anymore. In this course. Time?
That's just T.
Angular.
I thought you were asking for the symbol. I'm sorry.
What is the rotational analog of time?
Rotation. Revolution.
Time.
Period.
Time.
It's just,
Well, I
Yeah.
mean, obviously I knew it, I was joking.
Right.
No, but like, I'm taking jokes. No, I think it's
Whether something's rotating or whether something's traveling in a straight line, time is the same, especially in classical physics. So time.
Why does all the rotational and angular stuff have a vector sign over it?
Because they're vectors.
How is an angle, okay.
the same way 0 can be a vector. Which is not at all making sense, but yeah.
All right, we'll get into the direction in just a moment. All right, so first off, in terms of equations, so we haven't completed our list over there, but at least we can get as far as doubling all the equations from the chapters 2 and 3. So I know that delta S is equal to VIT plus 1/2 AT squared. And to double this equation, since the math behind it is similar, we just do transliteration. So instead of position using S, we'll use theta. So delta theta is equal to omega I t plus 1/2 alpha t squared. And so this is how we're doubling it. We just take the old equations that we have been using and we're going to stick in the rotational analog.
Yeah.
Let's take Vf squared equals Vi squared plus 2A dot delta x, that's whatever you're using. What would the rotational analog be?
Omega final squared equals omega initial squared plus 2 alpha times theta. Whatever, displacement theta?
Delta theta?
Oh, sorry.
Is that a U with like an unfinished umlaut, or is that an I next?
This?
Yes.
It's an I.
Do the other cake formulas apply to this?
Yep, absolutely.
Could you write them all down for me?
Hold on. Yep. All right, so here's a chapter 2 problem. Ball traveling in a straight line, initially going -4 meters per second. After having a displacement of positive 20 meters, it is going 40 meters per second. What is its acceleration? It's just a straight up plug and chug into this formula right here.
Right.
So we have 40 squared is equal to 4 squared plus 2a times 20. Work through the math and you get something.
Yeah.
640?
Yeah.
Are you just saying yeah?
Yeah, cause I believe in you.
It may or may not be right. That is not right. I appreciate the faith though. So that would be 40 minus, so it's gonna be 39 point something. 39.4? 6 meters per second squared. All right. Let's make it a chapter 9 problem. All right, questions on this before we look at it from a chapter 9 point of view?
Evolves traveler and then, oh, sorry.
Hmm?
Circle.
No, it's like
Marker.
Is it?
All right, so we will just change out ball for a wheel. Is rotating on a fixed axis. Initially going -4 radians per second. After having a displacement of, or after having an angular displacement of 20 radians, it is going 4 radians per second. What is its angular acceleration? 39.6 radians per second squared. It's the same math problem. And I haven't really gotten into what a negative 4 radians per second is versus a positive 4 radians per second.
Just counterclockwise, right?
Not necessarily.
No.
Is it
As
one
much
of the
as
clock-
I had is always to the right,
Is it one of the clockwises?
from someone's point of view.
Wow, thank you.
Well, I mean, if you want something more specific, is that clockwise or counterclockwise?
For me, it's clockwise. For you, it's counterclockwise.
Yeah, so if it's like this, clockwise or counterclockwise? Well, it depends upon where you're standing. So we have to somehow resolve that so that we're not having to use a whole lot of extra words of, it's clockwise when you're standing on the ceiling, when you're plastered on the ceiling looking downwards. We need some better way of doing that.
Instead of displacement, what does it say? Instead of displacement, what do you?
Wouldn't it be what?
Angular displacement. He added angular.
Yeah, the angular displacement. Okay, so we've gotten this far. We've got the 2 other cake formulas, which you can just plug in the proper omega, alpha, or theta. Yes?
I regret to say this, but I've forgotten the 2 other cake formulas.
We have delta S equals VI plus VF over 2 times time. And V final equals V initial plus A T.
Thank you.
So that only doubles the number of equations we have for the first 2 chapters we dealt with. What about the fourth stuff? Well, yes, we're alive.
Oh, I thought we were gonna.
There, we're gonna what?
I thought we were just gonna ignore the forces.
No.
Oh.
Yeah, go chapter 9.
Is this chapter 9?
Yes, chapter 9. All right, so the rotational, or the linear dealing with force, you have a force which might cause acceleration. But there's gotta be something that might cause angular acceleration. And that is known as torque. symbol for torque
Yeah.
is a tau.
It's what?
Tau.
Oh, Tom.
Now, I would say it's my most obscure, it was at one point my most obscure reference, but I also sometimes will refer to torque as G2 Kombuko.
Is what?
G2 Kombuko. But strangely,
G2 Kombuka?
G2 Kombuko. Strangely, I've had two students who actually knew the reference. This would have been an obscure reference in the late 80s when it was more current. However,
What's it from?
I will not explain it.
Sounds like it comes from Jumanji or something.
So, oh, there's one more that we definitely need to do. Mass. There is a rotational equivalent to, or analog of mass, and it has two names that I will flip back and forth between them. I tend to use the term moment of inertia because of typical childhood scars. But it's also sometimes referred to as rotational inertia. Don't care for that as much, but I have seen that more within the past 10 years.
So mass and its counterpart is moment of inertia?
So the rotational analog of mass is rotational inertia, and the symbol is, we will now break our Greek letter pattern, and it is a capital I.
Moment of inertia, rotational inertia.
Yes.
So mass is its counterpart then?
Yes.
Yeah.
So if we take Newton's second law, this is great if you have a bunch of forces acting on an object and we want to see how is the center of mass of the object accelerating. However, sometimes we need to deal with things